what is located all along that curve, like between the 0 and the 1? You know how you have your curve, and you have your standard deviations, you put your mean. You have your standard deviations here of 0, 1, 2, 3, and -1, -2, -3. Well, there's all numbers in between those lines, right? So there's other numbers besides -1, +1, 0, 3. There's all those numbers in between. For instance, say I had a test score, a mean of 80, makes 70, and a standard deviation of 6. So this would be 70, 76, 82, 88. I work my way down, 64, 58, 52. So I know what my z-score is. These are our z-scores down here. I know that a test if a test comes in and it's a 70, it has a z-score of 0. Don't I find that right on my chart at the middle? It is the mean. So my standard deviation says it didn't vary off my mean at all. It was at 0, right? If I had a test of 82, I could follow it down. I'm 2 standard deviations above the mean. True? My z-score is 2. We just put all these standard deviations above and below the mean as a z-score. Now, what happens if I have a test of 85? 85 says, okay, well, I can kind of add these. I could come smack in the middle, right? And I have 2.5. I have 2.5 standard deviations above the mean. My z-score is 2.5. What happens if I came through with a test score of 86? It's there. Isn't it right near the 2.5 somewhere? It's there. But I can't really say it's 2.5. I can't say it's 2.6. I have to have a way to find them. They exist. It's a continuous curve. So we have a little formula that we use. We have a little formula that we use to get all those scores in between. And it's called your z-score formula. Okay, this is a little formula that we'll use. Now, when you take a look at your z-score, if you take a look at page 107, it says the standard score, what we call the z-score, represents the number of standard deviations that a value x lies from the mean mu. To find the z-score, we'll use this formula. So again, if I knew my test score was 82, it lies 2 standard deviations above the mean for a z-score of 2. If it lies at 85, we can estimate that one to be smack in the middle. Our z-score is 2.5. Oh, excuse me. Other ones to the positive negative. If my test score is 64, it lies -1. It lies 1 away from the mean on the negative side. Our standard score, our z-score, is -1. So if we have something like 86, we're going to follow this formula. X is the test value. So we're going to say 86 minus my mean, which happens to be 70, over my standard deviation, which was 6. So we put this in your calculator, and we get 16 divided by 6. You have to let your calculator do it. And we get a z-score. And your z-score is 2 decimal places. So this comes out to be 2.666 repeater. You round it to 2 decimal places. So you have a z-score, a standard deviation of 2.6 standard deviations away from the mean. Why this sketch is important is because we get negatives as well. Say I want a test score of 59. My test score of 59 falls here. Shouldn't my z-score be negative? Right? So when I do my formula, I say x minus the mean over the standard deviation, and I'll get a negative. Now, this is the one formula that I need you to remember. All the other formulas that we have to use, I pretty much give you. But this formula, I need you to remember. But this is how easy it is. How do I remember which way to subtract? Because if I need a negative, I subtract the smaller minus the larger. If I need a positive, I subtract the larger minus the smaller. Doesn't that make sense? So if I tell you, and you can't remember the formula, I tell you I have a test score of 62, and you say, okay, 62 should be negative. Oh, I subtract the smaller minus the larger over the standard deviation. And that's your x minus your mean over your standard deviation. Okay? So z-scores give a placement on this standard deviations chart. All your standard deviations above and below the mean, we will call your z-scores. If you open your book, let me see if it's in front of your book as the other ones were. They put it in front of the book. No. If you turn to page, you guys probably have these flip outs attached to your books in the back. See these flip outs? If you should, right? At the very back, it should be attached to your book. There's a bunch of tables on these, a bunch of formulas. No?
No.
You guys don't have a flip out, just me? Wow. Okay, so if you guys turn to page, I'll tell you 1 second. If you guys turn to page A16, it's got a blue binder, a blue page border in the back. A16, that's your table 4. That's your z-scores. Now, what we get from this, and I told you after we learn this, you'll never have to worry about using your chart with the 34, 19, and all those other percents there. We use this table. So say I want a z-score, and I want to know, we always read the area to the left. I want to know what area this is. Instead of having to add up all these things, I come to my z-score. Say we looked up a z-score of 2. I come to my z-score of 2, and if you just follow the table on A17, come down to 2.0, come across to 0, 0, and 0.9772, that's the area that you've added up from here to here. We use this table to get there. If you're looking for, you know how we added up your area on your curve?
Yeah.
Right? So I no longer have to use my curve. If I wanted to, like say my standard deviation is 2, instead of me going to say, oh, add up all of those pieces, I go to this chart and I look up 2.0, look it up on the positive side. It's got a negative and a positive side. So it's 2.0, the one across the top gets you the hundredths place. So 2.00 gives me an area of 0.9772. That means 97.72% of your data falls to the left. That means that's at the 97.72 percentile. This is where your percentiles come in, from 0 to 100. Your whole area under your curve is 100. So if I figure out all the area that I've covered from here to here, that's my percentile as well. I get the area under my curve and my percentile. Right now, we're not as worried about the table as we are getting you used to just looking at the z-scores. After we hit probability, we go back to this table and we do a lot more with this table for the rest of the course. But I want you to see a connection so you have a better idea of what's coming down the line here and how all this ties into place. Now, according to your chart here, your z-score has certain attributes to it. Okay? If your z-score is negative, and this makes sense, it falls to the left of the mean, true? The standard deviations to the left are negative. That's where we locate our z-score. If your z-score is 0, up, that means you're right at the mean. You haven't deviated off the mean at all. So your standard deviation is 0 away from the mean. So your z-score is 0. Not your standard deviation, but your z-score is 0. If your z-score is positive on this side, that means you fall to the right of the mean. That means your x value is greater than your mean. True? All I want you to do is make sense of this today. It makes sense, but you have to make sense of it. So what we do is get a placement so that we can figure out what's going on. So let's work out an example together. Example 7 on page 108. Example 7 says, and always pull out your information. Pull out your mean, pull out your standard deviation. Mean speed of a vehicle along a stretch of highway is 56 miles per hour. Mean is 56, standard deviation of 4 miles per hour. Pull these out first. You measure the speed of 3 cars traveling along a stretch of highway. The first one is at 62 miles an hour. The second one is at 47 miles an hour. The third one is at 56 miles an hour. 108. You want to find a z-score that corresponds to each speed. Now, in your notebooks, I want you to do this with me. Let's make a graph first. Let's make our sketch. In the middle, this is where your mean is. The mean is 56. Give me 3 bars, 1, 2, 3, and 3 negatives. Okay. So let's take your mean, and let's go up 4. 60, 64, 68. Everybody okay with this? Let's go down 4. 52, 48, 44. We started at 56, that's where your mean is. We added 4 all the way up, we subtracted 4 all the way down. The standard deviation was 4. These are your z-scores located down here. Now, I remember last week, I don't remember who it was, but said, does it matter where I put my my x's and my numbers on the bottom? And I said it will soon. So here's why we leave your z-scores on the bottom. This whole area, like you remember, adds up to 100%. We want to find what's z-score, so we're going to take this guy, this is the x, and we're going to see where does this fall. So find me where it falls on your chart first. 62 falls between what 2 values? 60 and 64. So should that z-score be a positive or a negative? A positive. So we use our formula. X minus the mean over the standard deviation. X is your number 62, and you knew you had to subtract the larger minus the smaller because you told me this was positive. So we subtract them, and we get a z-score of 1.5. Good. We knew it would be positive because it's to the right. We knew when to get a positive, the larger minus the smaller. And we can pretty much almost tell that by looking at a curve, can't we? But doesn't 62 fall halfway between 60 and 64? So shouldn't that be 1.5? So we can pretty much tell that. Now we're going to take a z-score of 47. We have an x of 47. We're going to find its z-score. So let's locate it. 47 falls just to the left of 48. Should that z-score be negative or positive? Negative. Negative. So approximate. If you can approximate it, what would you say? Negative what? 2.2, 2.3, 2.1, somewhere in the negative 2 point something, right? So let's see what it becomes. We know that it's going to be negative, so remember, you subtract the smaller number minus the larger number. This is always your x. Always x minus the mean. But if you forget what order, you use your graph. If it has to be negative, the smaller minus the larger. So now, you subtract them, and you find your z-score. And you said about negative 2.3, negative 2.2, and there we are. Does this make sense? Yeah. So let's find the next one. This is all I have to get. Now we have an x value of 56. Where do we find 56? In the middle, it's the mean. So what will your z-score be? 0. So your z-score should be 0, so let's try. Your x, 56, minus 56 over 4. Yep, my z-score is 0. What's that? Well, yeah, but it kind of gives you a perspective on, but before you didn't call these z-scores. They were how much your standard deviations went to the right and to the left. So now that you'll know it's called the z-score, and you know this is half your curve, 50% of your curve is to the left, 50 is to the right, it kind of gives you a better feel for, you know, and believe it or not, for us kids that don't see it yet, so that, you know, it takes a little longer to like play with this curve and keep, you know, referencing it, getting a feel for it. I think the most important thing is that you make this sketch. You need to see where your negatives and positives are. You need to see those. Okay, so you guys are going to try this one. Try it. Oh wait, where are we? This one. You guys are going to try this one. I want to see a sketch on everybody's paper. Okay, so we've got a curve. What's the mean? And a standard deviation of 8. So 70. 78. 86. 94. 62. 58. Okay, now, we've got a score of 60. Should this be a positive or a negative? Negative, good. It falls to the left of the mean, right? So, 60 minus the mean over your standard deviation gives you what z-score? Negative 1.25. We're going to do 1.25. Sorry about that. Negative 1.25. And it makes sense to us. Here, guys, here's our 60 right here. See it? What happened here? This guy can't be 1.25, can it? Oh, I started that mine on the wrong thing. Okay, sorry about that. So there, it's over here. So there's negative 1.25. That makes more sense. So 62, 58, 50. Sorry about that. I had one too many lines. Okay, to make sure, this one terminated, but make sure I get 2 decimals because that's what your table uses. So now, the z-score of 71 should fall where? To the right or the left of the mean? To the right. How far to the right? Not far, just a little. So shouldn't my answer be between 0 and 1 somewhere? Closer to the 0? So once you get a frame of reference, and you come out with an answer, excuse me, that's not feasible, you say, oh, wait a minute, that can't be right. I expected it to be between 0 and 1. So you do this and you get 0.125, round it to 2 decimal places. I know it terminates at 125, but round it to 2. Your tables work off of 2. And your last one, when x is 92, approximately where should that fall? Between which 2 z-scores? 2 and 3, right? So it should be positive between 2 and 3. This is a good frame of reference. And what did you get for this one? 7.5. Okay? We're good with this? Yeah. Just get a frame of reference. One of the things that z-scores are good for comparing things that are different. Kind of like your coefficient of variation, how you compared your standard deviation to the mean, and you took a look at that, you did your coefficient of variation. This kind of does too. It says this. Let's take a look at one that makes a comparison. It says, Table 8, give me a couple minutes, guys, and we're almost done. Table 8 on 108 shows the mean heights and standard deviations for a population of men and a population of women. Compare the z-scores for a 6-foot man and a 6-foot tall woman. Now, they're both 6 foot tall, but according to the chart, the mean for the men is higher than the mean for the women. So they both have different z-scores, and they both have, one might be unusual, one might be okay, right? It's a way of comparing two different things. For instance, you take two tests today. You took a test in statistics, you took a test in biology or chemistry. In chemistry, you got a 54, but the mean for the class was 60, with a standard deviation of 8. Aren't you kind of close to that mean? You're close to the middle? You did better compared to you did a little bit worse than the mean, but you didn't do too far away. Say in statistics that you got a 95 and the mean was 50. And you do really, really well compared to what the rest of the class did. So even though you can't compare your two tests, if you compare your z-scores, which takes into account its own mean and standard deviation, you can say you did far better on your statistics test according to how your classes did, right? I mean, yes, your score appears far better, and sometimes we see it a little bit different. Say your mean was 70, you got an 80, okay? And then your standard deviation was, let's say, 2. In the next class, you got an 80, but your mean was 75. You didn't do as well, even though you still got both 80s, right? So do you see what I'm saying? You can compare two different kind of groups using your z-scores. The higher the z-score, the better it is. The higher that you got away from the mean. So this one tells us to compare the 6-foot man's height to the 6-foot woman's height. So we're going to take the men's height. These are your men, these are your females. And we're going to see who actually is more closer to the mean and which one is more unusual. So if we chart your z-scores for these guys, both of them had 6 foot. How am I going to set up my z-score formula for men, for female? How would I set this up for the male side?
2 minus 69.9.
Good. So Olga remembered, these are feet, these are inches. So switch this to inches. 72 minus 69.9. You're still well above the mean. What does the z-score come out to be? This one?
No, 0.70.
Okay, because it's very close to the mean. Here's my mean, 69.9. Here's my one, 72. It's very close to the mean. Would you consider this an unusual height for a man?
No.
No, this is not an unusual height. Now, the same size female says, find me the z-score. 72 again, minus 64.3 over 2.6. They have a little less spread in their heights. What is this z-score? 2.96? Now, look how far away that is from the mean. Is that considered unusual?
Yeah.
Yeah, that's almost very unusual. Plus or minus 2 away after 2 is unusual. After 3 is very unusual. So this is unusual to get a female who's 6 foot tall, yet it's not unusual to get a male who's 6 foot tall. And they are the same height. I mean, yes, we can visualize that ourselves, we can understand that. But in terms of finding your z-scores, doesn't it make sense? Yes? Okay, you guys are packing up. You got a few more minutes. 5. Okay, try one more for me. One more and we call it a day. Use these.
Oh yeah.
Come on guys. Use the same chart and compare two 5-foot people. 5-foot male and a 5-foot female. And let's see where they compare in their own categories, if it would be unusual or not. You're going to do the same situation, but instead of using 6 foot, you're going to use 5 foot. How many inches? The same name as in your book. The chart. Same name. Yeah. Mhm. How many inches is 5 feet?
60.
60 inches. Good. 60 inches.
I'm shocked.
Okay. Demani, it's the same
Oh,
name.
I got it.
This table right here. You're going to do the same thing, but now your X is going to be for this guy, 60 inches, and for this female, 60 inches. Now they're the same height, right? But compared to their category, we want to see who is unusual and who is closer to the mean.
It's the mean. The mean is 69.9.
Yes,
Okay.
same situation.
Yeah.
So this Z-score is going to say 60 minus 69.9. Are they below the mean or above the mean? And what's their Z-score? Ah, is that unusual? Very unusual. Okay, this Z-score says 60 minus 64.3. Is this below the mean? Still below the mean. And what's their Z-score? Okay, not as unusual, right? So even though they're the same height,
So the closest you get to
yeah, plus minus 1 is where your normal business lies, because that's the biggest part of your mound. As you go out, it's a 2, plus minus 2 is unusual, plus minus. And by the same thing, if we had someone who was tall, that's unusual the other way, this one's shorter, unusual this way. Okay, Monday, guys.